Welcome back to Inspire AI, the show where we explore how leaders, creators, and innovators are shaping the future with artificial intelligence. Imagine standing on a foggy mountainside, trying to reach the valley below. You can't see the whole landscape, but you can feel which direction slopes downward under your feet. So you take a cautious step in that direction, then another, adjusting as the ground tilts. This simple intuition, step by step moving downhill, captures the essence of what data scientists call gradient descent. In this podcast episode, we'll demystify gradient descent, the unassuming algorithm that powers how AI learns. We'll explore it in accessible terms, no dense math. We'll discuss why it's crucial for modern AI, especially neural networks. We'll highlight real-world applications from movie recommendations to self-driving cars. We're going to trace its evolution from 19th century idea to today's advanced versions like Atom and RMS Prop, and candidly examine its limitations, like getting stuck on hillsides or the need to fine-tune knobs. The goal is a compelling journey for all listeners, whether you're a student, developer, an executive, or just curious about AI, to understand why gradient descent is like the steady downhill walk that teaches machines to be smart. So let's dig in. I'm going to start us out with a conceptual picture. Again, think about an AI model learning as an explorer in a hilly terrain at night. The height of the terrain represents the error or loss of the model. Higher means worse performance. Lower means better. Gradient descent is the strategy the explorer uses to find the lowest point or the minimum error without a map. So as the analogy of hiking to the valley resumes, the model checks the slope of the ground under it, calculates the gradient of the loss. If one direction slopes downward most steeply, that's the way to step next. Take one step. Adjust the model's parameters. The model parameters are the internal variables in a machine learning model that are learned from the training data. They determine how the model makes predictions or classifications. And there's a couple that you might run into if you ever talk about this with anybody. First type of model parameter would be weights, where these are numerical values assigned to the input features, what goes into the model, that is, to be trained, and the influence of the output based on the importance of each feature. So I guess you could say the heavier the weight, the more important the parameter is, or the feature is. And then there's also biases. The biases are additional numbers added to the model's output to adjust predictions independently of the input features, hence the name biases. These things are important to understand because during the role in learning, training, if you will, the model adjusts its parameters to minimize the difference between the predicted and the actual outcomes. And they are used during the optimization of the algorithms because during training, the model adjusts its parameters to minimize the difference between predicted and actual outcomes, often using optimization algorithms like gradient descent, which we're diving into now. So as the steps are taken, the model's parameters are adjusted slightly, and then it recomputes the new slope at the new position. So by repeating this step-by-step descent, the model gradually improves, much like an individual feeling their way down a mountain path. Initially, the steps might be large and the descent steep. Later, they become small as the ground flattens out near a valley, where we might deem that as the minimum loss or error in the prediction. This process continues until the slope is almost zero, meaning you've reached a low point and further steps don't improve things. What you can't do during this metaphor is jump straight down to the bottom because you're never sure what lies directly ahead during this process. By always stepping in the steepest downward direction, you eventually reach a valley. In machine learning, that valley is a set of model parameters that yields the lowest error on the training data. And this intuitive downhill approach is how a neural network tweaks its internal knobs or weights to learn from the mistakes. Each training example or batch, the network calculates in which direction, with respect to each weight, the error increases, and then nudges the weights the opposite way, going downhill on the error surface. In essence, the gradient descent is the AI's learning process, converting feedback errors into incremental improvements. Just like our hiker uses the slope as feedback to find lower ground. So I'm oversimplifying things here, and it may sound simple, but it's truly the workhorse of modern AI. It's the learning engine under the hood of virtually every advanced machine learning model. So in fact, this algorithm quietly powers neural networks, recommendation engines, language models, almost every major AI breakthrough of the past decade. Without gradient descent, training deep neural networks like those behind image recognition, speech to text, or intelligent chatbots would be infeasible. So if you walk away with anything here, it's gradient descent is like the backbone of the neural network training, and is by far the most common method of optimizing neural network models today. Every time a neural network adjusts its weights via backpropagation, which I'll explain in a second, it's using gradient descent to incrementally reduce error. Okay, what's that term I just said? Backpropagation. Well, it starts with neural networks. They are like brain-inspired math machines. They learn by trial and error. And as they try and error, they have to figure out somehow what to fix when something goes wrong. Backpropagation, it is the math magic behind almost every AI breakthrough today. I'm not going to really get into the deep technicals here. Probably scare off most of my audience, but what I can say about it is that as it's flexing its brain muscle, it's taking guesses in the forward path. So it tries to figure out through the layering what inputs to use, what weights to apply, what biases to correct with. And at the end, there's an output prediction. So that's kind of like step one. Step two would be a loss calculation, where it compares the network's guess with the correct answer using a loss function. Basically, it tells us how wrong the guess was. Then we work backwards, the part of backprop that really will stick in a second. We apply the chain rule from calculus to compute the gradient, which tells us how much each weight contributed to the error, right? These gradients guide how to update the weights. And then finally, we update the weights. This is the system's nudge, the nudge of the weights, using gradient descent, moving in the direction that reduces the error. A key setting here is the learning rate, and it controls how big each update is. I'll talk a little bit more about that in a minute. So this method of gradient descent scales to massive data sets. You've heard the term billions of parameters, trillions of parameters. Updating the model parameters iteratively rather than requiring a closed-formed solution. This technique is like a mini batch. With techniques like mini batches, it can handle millions of data points by taking many small steps. This scalability is one reason deep learning exploded. Gradient descent made it practical to train on huge data sets gradually. And what's great about it is that it's not even tied to one kind of model or task. As long as you can compute the gradient of your error, you can improve the model. It works for linear regression, logistic regression, support vector machines, and all flavors of neural networks, from convolutional neural networks to transformers. It's the common learning method across these diverse algorithms. So in short, gradient descent is how AI models actually learn. The fancy structures of deep learning, like millions of neuron connections, would just be static random weights without gradient descent to tune them. With gradient descent, every mistake the model makes turns into a useful signal, a direction to adjust the model parameters so that the next time the error is a little less. It's hard to overstate its role because without gradient descent, there would be no modern AI training, no tuned neural nets powering vision or language tasks, period. So, how does this abstract downhill optimization show up in the real world? In truth, almost everywhere that AI is making an impact. Gradient descent trained models are behind many technologies we use daily. So here's a few examples spanning both everyday consumer tech and cutting edge systems. First, search and recommendation systems. Ever wonder how Netflix knows what show you might like or how Google ranks search results? Machine learning models optimized via gradient descent are the answer. For instance, popular recommendation engines like YouTube, Netflix, and Amazon use algorithms trained by gradient descent to match content with your preferences. As they go, they adjust their model's parameters to minimize the error between predicted user ratings and actual ratings, gradually improving recommendations. Similarly, search engines train ranking models to give you more relevant results by minimizing a loss function that measures result quality. How about autonomous vehicles and computer vision? When a self-driving car sees a pedestrian or decides how to steer, it's thanks to neural networks trained with gradient descent. As an example, the vision system in a self-driving car is trained via gradient descent to detect pedestrians and obstacles. The training process tweaks the system's convolutional network parameters until it reliably recognizes objects in camera images. Beyond cars, any computer vision task, whether that's facial recognition, medical image diagnoses, uses models whose millions of parameters were optimized by gradient descent to maximize accuracy. All right, one more example. Robotics and games. This is where reinforcement learning kicks in. So even in scenarios where an AI learns by trial and error, like a robot learning to walk or game AI mastering a video game, gradient descent often plays a role. In reinforcement learning, after many trials, the algorithm uses gradient descent on a defined loss or reward signal to improve the policy or value estimates. Some landmark examples include DeepMind's AlphaGo, which uses gradient-based optimization to refine its neural networks that decide moves. So whether it's a chatbot conversing or a robot navigating, if the system improved by learning from data, gradient descent was likely doing the heavy lifting during training. Virtually any domain leveraging machine learning is indirectly leveraging gradient descent, from web services to healthcare. It is the invisible optimization engine enabling AI applications to get better and smarter with experience. So next time you see an AI-driven product that seems to get it right, there's a really good chance gradient descent helped tune it to perform that way. Gradient descent may be central to today's AI, but it's hardly a new idea. Its roots go back over a century, and it has evolved significantly over time, especially in recent decades, to meet the needs of deep learning. So here's a quick tour through the history and key improvements. In 1847, the birth of steepest descent, where the core idea was first proposed by French mathematician Augustin Louis Cauchy. He described using the gradient or steepest slope to find minima of functions, essentially the mathematical foundation of gradient descent. Back then, it was a tool for solving equations and optimizing math problems. Definitely not for machine learning as we know it today. Through the early 1900s, gradient descent was studied in numerical analysis. Variants like conjugate gradient emerged for solving linear systems faster. By 1944, researchers like Haskell-Curry were analyzing its convergence properties. It was a known optimization method, but computers were not yet powerful enough for the massive iterative training we do now. And as we all know From the 60s to the 80s, we enter the machine learning phase. As simple neural networks were developed, the idea of using gradient descent to train them took hold. In particular, the backpropagation algorithm, as talked about before, and popularized in 1986, relies on gradient descent to adjust weights in multi-layer networks. During this period, often dubbed the first and second wave of neural nets, researchers adopted gradient descent for training neural networks once they realized the power of using calculus, gradients that is, to improve model parameters. The method gained recognition as a viable learning rule for AI, although neural networks were relatively small then. We fast forward to 2010s, where the deep learning revolution really took hold. As datasets and models grew, plain gradient descent struggled with speed and stability. That era brought a flurry of advanced optimizer variants to make gradient descent scale to deep learning. Researchers start discovering adaptive learning rates, where algorithms like AdaGrad and RMSprop allowed the step size, or the learning rate, to adjust automatically for each parameter. RMSprop, for example, keeps track of recent gradients and divides by a moving average of their magnitudes, so it takes smaller steps for parameters with high variance gradients and larger steps where gradients are consistently small. This adaptation keeps training stable, even if some dimensions of the error surface are steep and others are flat. And there's a hugely popular variant called ADAM, short for adaptive moment estimation, where it combines the benefits of momentum and RMSprop. ADAM treats each model parameter as having its own personalized learning rate, adjusted based on both the recent gradient trend, momentum, and the gradient's variability. So in non-technical terms, it's like giving each weight its own paced descent. If one parameter consistently needs gentle updates, ADAM will automatically use smaller steps for it, whereas another parameter might get larger, momentum-boosted steps. ADAM and similar optimizers dramatically improved training efficiency for very deep networks and are now standard in training cutting-edge models. And as we continue to evolve our understanding and use of gradient descent, researchers continue to explore new optimizers and tricks, but they're all evolutionary improvements on the same idea of following the gradient. The algorithm from 1847 has become the keystone of modern AI, guiding trillions of parameter updates in large-scale AI systems. So despite its success, gradient descent is not a magical silver bullet. It comes with practical challenges and limitations that AI practitioners must navigate, especially as we build ever larger and more complex systems. So I'd like to talk about a few key constraints and why they matter for scaling and innovating future AI systems. First, computational cost and scaling. Gradient descent's iterative nature means training can be very slow or computationally expensive, especially for big models and datasets. Each step requires computing gradients, for which a large neural network means a lot of matrix calculus. When you have billions of parameters and terabytes of data, the sheer number of steps to converge can be immense. Moreover, gradient descent is inherently sequential, step by step, which makes it harder to fully parallelize. Researchers have developed ways to distribute training across multiple GPUs or machines, splitting data across many batches and asynchronous updates. But doing so introduces complexity and instability. The bottom line is this: to train cutting-edge AI, these giant large language models that we're getting so used to, you need vast computational resources and time. The cost is a major bottleneck. This challenge spurs work on more efficient training methods and hardware accelerators. There's a constant push to make gradient descent faster and more scalable. But as of now, training the state-of-the-art model can take days or weeks on specialized hardware clusters. They also have a sensitivity to hyperparameters. What I mean by that is gradient descent doesn't operate in a vacuum. It has knobs we must set, and these hyperparameters can make or break the training. The most infamous is the learning rate, or the step size. Choose it too high, and your steps are too large. The algorithm will jitter around or diverge, never settling into the valley. Just imagine our hiker taking leaps and overshooting the valley. Choose it too low, and the progress becomes agonizingly slow, like inching down the hill and possibly getting stuck in gentle slopes for ages. Finding the right learning rate often requires experimentation or schedules that change it over time. And there's other hyperparameters that include things like momentum and batch size. Gradient descent can be quite sensitive to these settings as well, where a wrong choice can lead to low performance, poor performance, or slow convergence. So all of this means that training a model isn't fully automatic. It often needs human or automated tuning of these hyperparameters to get the work done and to get it done well. This trial and error aspect is a limitation in the sense that it's obviously time consuming and requires expertise. A lot of the research is going into methods to make training more robust to hyperparameter choices. Adaptive optimizers like Atom were created partly to relieve the burden of picking a perfect learning rate. My last example of practical challenges and limitations is where we have very deep networks, which just means there are many, many layers of neurons. This is where we're going to encounter issues like vanishing gradients. The gradients become extremely small in early layers, so they hardly learn, or exploding gradients. Values diverge in huge numbers. These are specific technical problems often tackled by architectural tweaks, but they illustrate that gradient descent's effectiveness can degrade in certain settings without additional strategies. So if you think about it, gradient descent only finds a minimum in terms of training loss. It doesn't directly ensure good generalization, meaning performance on new data. Proper validation is needed to avoid overfitting, even if gradient descent optimizes the training error perfectly. Overfitting occurs when a machine learning model learns the training data too well. It captures noise and outliers instead of underlying patterns. This results in high accuracy on the training set, but poor performance on new unseen data. To summarize these examples, gradient descent has limitations that researchers and engineers must work around. It can be slow and resource hungry. It can get stuck or give diminishing returns if not configured right, and it requires careful tuning. These challenges are active areas of improvement as we push toward ever larger AI models. Innovations like better optimizers, second-order methods, distributed training algorithms, and automated hyperparameter tuning are all essentially attempts to keep the gradient descent process reliable and efficient at scale. Understanding these constraints is crucial because it reminds us that while gradient descent is powerful, making it train a 175 billion parameter model, well, is a delicate engineering feat and not a trivial downhill stroll. Gradient descent is nothing more than a humble algorithm with an outsized impact. It's amazing that such a simple idea iteratively takes steps in the direction that reduces errors, underpins the most advanced AI systems on the planet. From the way your email spam filter improved, to how an autonomous car learns to brake, to how a chatbot became fluent, it all comes down to this steady downhill optimization. Thinking back to our analogies, like walking in the fog to build an intuition for gradient descent, highlighted its critical role in enabling neural networks to learn. And in this episode, we traced gradient descent's lineage and improvements over time, and we confronted the practical challenges in using it for ever bigger AI ambitions. What did we learn today? Without gradient descent, there would be no modern AI as we know it. No deep learning breakthroughs, no intelligent systems improving with data. Yet gradient descent isn't magic. It's a tool, one that developers must wield with care, tuning it, scaling it, augmenting it with enhancements. As AI continues to advance, we'll likely see new optimization tricks and maybe even fundamentally new learning paradigms. But for now and the foreseeable future, gradient descent remains the dependable workhorse that is quietly enabling machines to get smarter. It's the slow, steady walk downhill that has led us to astonishing heights in AI capability. So next time you hear about a fancy AI model, you'll know that behind its intelligence, there are a lot of diligent, hill descending going on, one small step at a time. Until next time, I'm Jason McGinty, reminding you to stay curious, keep innovating, and always look for ways to future-proof your knowledge.